1997, number 7, part A. We want to know what the sign of delta S is for the reaction. So it's going to be a qualitative idea, and we're going to look at the reaction up here. And you remember the whole idea is delta S will be positive, and that's probably the easy part of the answer, because, and we've got to come up with some reasons for that. So I'm going to write down an explanation. Alright, so delta S is positive because the system is decreasing in order, so that's the reason why, and the evidence for it is there are more moles of gas on the product side than on the reactant side. And it might be better if you actually said how many moles. There's 1 mole of gas on the reactant side and 2 moles on the product side. Actually, I just read the key, and the key says that you do need to actually mention the number of particles. So that's something that I would definitely do. I would not have gotten credit for it. So I think that's a lesson for us. Be very specific in your answer. Alright, so in part B, they want to know what change will occur to delta G for the reaction as the temperature is increased. You'll notice that we already know delta S, and we even know something about delta H, because if we look back at the beginning, that more products are produced as the temperature is increased. So what that lets us think about is if we put energy into the reaction, we can figure out what the sign of delta H is. So as the temperature is increased, we get more products, which means it's shifting to the right. That means that energy must be, and I'm just going to put an E here, energy must be on the reactant side, because as we increase the temperature, it shifts to the right and we get more products. That tells us, since energy is on the reactant side, that energy is being inputted into the reaction. So delta H is positive, it's endothermic. So we now know that delta H is positive, and delta S, we just predicted a moment ago, was positive, and we're trying to interpret what's going to happen to delta G. Well, if we do that, we need the Gibbs-Helmholtz equation. We know that delta S is positive, delta H is positive, and there are a couple of ways that we could explain it. Maybe we'll try it mathematically this way. This whole term here is going to be overall, since S is positive and there's a negative sign out front, it's a negative, which is definitely favorable for delta G being spontaneous or favorable. Delta H, though, being endothermic, is definitely unfavorable. So an increase in temperature will increase the magnitude of the entropy term and cause delta G to become even more spontaneous. So let's find a way to explain it. Alright, so here's my explanation. An increase in temperature will, got a little typo there, we should do will, increase the magnitude of the favorable entropy term. So we're talking about that. Because of the negative sign in front of the entropy term, delta G will become negative. So I think that's a good enough explanation. And look at the key online and see if it matches up with what they're doing. But I think that should do it. Actually, when I'm looking at the key, I probably should have put right in here will become more negative, because you notice they're talking about the change in delta G. Not just negative, it's becoming more negative as you increase the temperature. Part C is asking about helium gas being added to the reaction mixture. Remember, the key thing to remember there is that helium is an inert gas. It does not react. So this is kind of a refresher from way back in equilibrium. You remember that an inert gas does not shift the equilibrium either way, and so it would not affect the partial pressure of chlorine because you wouldn't make any more chlorine or less chlorine. So let's find a way to explain it. So I said helium is an inert gas and will not shift the equilibrium. Therefore, no change in the partial pressure of chlorine will occur. You know, one thing that they say in the key, and I kind of agree with, is you might want to explain why, and definitely the one they pointed out is probably a really good one, which is helium is not in the equilibrium expression, which kind of is the explanation of why it won't shift the equilibrium. Oops, in the equilibrium expression. I think you would have gotten credit for it without this, but it's definitely a good add-on. Part D. If the volume of the original reaction is decreased at constant temperature, so the volume is decreasing to half its original volume, what will happen to the number of moles of chlorine in the reaction vessel? So you remember that if we're decreasing the volume, so we're going from something like this to something that's half its size, we are going to end up condensing those guys. So as the volume decreases, the pressure will definitely increase. We're kind of seeing at this point that it's really difficult to separate thermodynamics from equilibrium. So you remember the idea here is that if the pressure is increased, Le Chatelier's principle will try to relieve that pressure by shifting to the side that has less moles of gas, because there's too much pressure in here, and if it shifts to the side with less moles of gas, it can relieve that pressure. Well, in the reaction up here, that means it's going to shift this way, because there's only 1 mole of gas on this side, but there's 2 moles of gases on that side, which means it's going to shift away from chlorine. We're going to expect to have less moles of chlorine. So let's try to come up with an explanation. Alright, so here's my explanation. A decrease in volume will cause a momentary increase in pressure. According to Le Chatelier's principle, the reaction will shift left toward the side with less moles of gas. Therefore, the moles of chlorine will decrease. Now when I look at this, before I go look at the key, I'm a little bit worried about a couple things. One is, I'm getting the feeling that this is a qualitative question, because you notice there's not a lot of calculations in it. But the fact that they said a very specific amount, it's cut to half its original volume, worries me that they really want to know a quantity. But I doubt it. So I'm going to go look at the key and see. Alright, so I checked the key and they did not require any numbers. But you'll notice that they say that a statement of Le Chatelier's principle in and of itself is not enough. And what they mean by that is, this is the key thing here, toward the side with less moles of gas. If you just say it'll shift according to Le Chatelier's principle, that's not good enough. You have to say why, or how you predicted it. So that's kind of the important part.